There we go. All right. You're good to go.
Thank you. Hello, everybody. Welcome to the November Gazebo community meeting. And let me start. Welcome everybody and share the screen to show you the agenda for today. We'll start with announcements. There are a bunch of things after Roscon. Adiso will go over there. And also a new challenge using Gazebo. And then we have our invited speaker today, Elena, which will go over her work during the Google Summer of Code using or designing or porting pretty much like an existing sensor to Gazebo using CUDA. Are you ready, Adisu? Okay, so let's start with the news.
All right, thanks, Carlos. Hello, everybody. News for this month. We just had Roscon, so there's a number of talks from the Gazebo team that I invite you all to take a look at. The Gazebo project update was given by Steve Pierce, and it talked about what happened for the Jetty release, but it also has some of the roadmap items, initial roadmap items that we're going to work on for Gazebo Cura, realistic terrain simulation in Gazebo by Ian Chen, and Jen Nguyen talks about how to use texture maps to simulate different types of slip behavior on height maps and different terrains in Gazebo. Ray tracing everywhere uses WGPU, which is a tool from the Rust community to create a ray tracing based LiDAR sensor, which is high performance and vendor agnostic. And this is something we're exploring coming down the pike for Gazebo. This is an early experiment, but something we're looking at more closely. Last but not least, Ian Chen from Gazebo team and Adam Dabrowski and Ayush Josh presented the new raw simulation standard interfaces, which are messages and services in ROS that allow you to use different simulators, easily swap out different simulators, and be able to control simulation and state and control the evolution of simulation from ROS easily. So yeah, take a look at those Roscon talks. The other item, news item here is Intrinsic is running this AI for Industry challenge. It is a challenge where we're trying to tackle this assembly task, assembling cables and managing cables and doing insertion. It's very difficult, and we want to get people involved and collectively solve that problem. $180,000 in prize money, and it's going to go through 3 phases. The first one is competitors will train their model using any of the tools that they want. You can use Gazebo, or you can also use Majoka or Isaacson or whatever tool you want. But the model you create or the submission you create will be evaluated using Gazebo. And then in the second phase, those who do well in the first one will go to the second phase, where they'll use the product, the intrinsic flow state product, to build a complete robotic cable handling solution using the models they developed from phase 1. And then the folks who advance from that go to phase 3, which will run on real robots at the headquarters at Intrinsic. And then, winners will be determined based on that. So, yeah, form teams. I think the the suggested way to do it is to form teams and compete so that you have much better lack of success. So we invite everyone to participate. So, and that is it from me.
Thank you, Adisu. Yeah, very interesting news at Roscon, of course, and also an interesting challenge. Well, we move to the next item in the agenda, which is our invited talk, and it's my pleasure to introduce everybody Helena Moyen from University of Sao Paulo in Brazil, and she was a Google Summer of Code student over the summer, and her project was accelerating physics-based multibeam sonar simulation for underwater robotics on CUDA. So she is going to go through the details of that project. So take it away, Elena.
Thank you, Carlos. So I will share my screen. Are you able to see it?
Yes.
Okay. And is my audio okay? Can you guys hear me?
Perfect.
Okay, so good afternoon, everyone, or good morning. I'm Helena. I'm a computer engineering student from Brazil, from the University of São Paulo. I'm also doing my master's here now in Italy. And today I'm going to present the Google Summer of Code project we developed this summer within Open Robotics. And this work is a continuation of last year's Google Summer of Code, which migrated Project DAVE to ROS2 and Gazebo Harmonic. And this year, the goal was to migrate and optimize DAVE's physics-based sonar plugin also for ROS2 and Gazebo Harmonic. And I had the guidance of my mentors, Wansug and Rakesh, and also a lot of support from community volunteers, Gaurav Kumar and Ashu Martin. So before going to the work, also feel free to interrupt me at any time if something is not that clear. I will present briefly the project DAVE. So DAVE stands for DAVE Aquatic Virtual Environment, which is an open source underwater simulation environment. It was developed for rapid testing and evaluation of underwater vehicles mainly, specifically for autonomous missions or manipulation. And it was built on top of ROS1 Noetic and Gazebo Classic. And it relied a lot on the UUV simulator. And last year we started migrating it to ROS2 and Gazebo Harmonic. And this year we focus on the Multibeam Sonar plugin, which is a very special plugin from this project. So what is this plugin? So what is the Multibeam Sonar plugin from DAVE? It basically is a physics-based, high-fidelity, real-time, forward-looking sonar sensor plugin. So it differs significantly from previous methods, which used to create this intensity range sonar image from pixel conversion from rendered images. And now Dave's plugin, the goal was to have a array-based model which would create more realistic plots like this one that describes the sonar raw data. And it also incorporates phenomena such as angle and time ambiguities, phase reverberation, and speckle noise, for example. So this plugin already had GPU parallelization, and our goal was not only to migrate it, keeping that GPU parallelization, but also to enhance it. So this is a summary of what the plugin used to look like. So we had some basic demonstrations, such as the sonar tank simulation with BlueView P900. It had a local search scenario here, where you can see the shadow of some objects on the sea floor. And it had XP validation, features like variation over effect, and also distortion resolution. For example, here you can see normal vase and a distorted vase and active sonar images from both of them. So moving on to our project this summer, we had three main goals. So the first one was migrating the sonar to ROS2 and Gazebo Harmonic by creating a custom Gazebo plugin. The second goal was to enhance the physics-based sonar simulation. So our question was, can we make it faster? And the third one is to develop installation methods for ROS Gazebo and CUDA, which we've done. We have a native installation and also a Docker installation. So the first part of this presentation, I'll focus on the migration and how it was done, and then I will move on to the performance improvements we did in this plugin. So the migration began firstly by having the idea of creating a custom sensor in Gazebo. So instead of relying on a depth camera or a GPU array sensor plus additional plugins and processing, we focused on creating our custom sensor in Gazebo. And we started from the DVL custom sensor example that's available in the Gazebo repository, and we striped down. So we did that because we had some difficulties creating a custom rendering sensor. So we started with the DVL, and we knew that that worked, and we simplified it and tried to adapt it to our purpose. And when the core was working, we combined it with the GPU array example sensor that's also in the Gazebo repository to create our point cloud. And the point cloud here is essential to create then the sonar image with the same physics pipeline as before. So we didn't change the actual physics behind it. We just now have only one custom sensor plus the system that we attach to the world where the sonar is in, instead of having the depth camera plus an additional plugin. So that's the main difference from the old DAVE sonar plugin. This is a diagram of the architecture. So here on the left, we have the Gazebo sensor, the sonar sensor shell. The important part to move on to the next step in the presentation is that this sensor shell calls the CUDA sonar calculation wrapper, which is a separate code, a CUDA code that effectively calculates the sonar raw data. So it returns a 2D complex value array representing the amplitude and the phase of the sonar data. And basically, these functions in green are the functions that we added. It will be more clear along the presentation. So this is the results of the migration of the Multibeam Sonar plugin. So just as before, we try to keep the demonstrations. So we still have the Blueview P900 sonar tank simulations where we have two cylinders, and you can see the point cloud in RVS2, the camera view, so what the sonar is watching and is facing, and the resulting sonar image here. We also have the local search scenario, just as before, where you can see the objects and its shadows in the sonar image. And we also tried attaching it to a blue ROV. And this demo is under development. So we want the blue ROV also to move. But for now, we just attached it to the model, and it works fine to gather the sonar data. We also have the distortion resolution, and we tested it with the same models as before. So for example, here we have the normal ship and the respective sonar image, and the distorted ship with the distorted sonar image here. So now I'll move to the performance improvement that we did. And for that, I'm going to do the CUDA code breakdown. So first of all, we have to keep in mind that the total plugin refresh rate before, so after migration, was 1.33 Hertz, an average per sonar frame. So this includes the CPU part, which does the ROS2 topic publishing, subscribing, and also the construction of the sonar image after the calculation of it, and the GPU part, which is the sonar wrapper that actually does the calculations. And this CUDA sonar wrapper is divided into these 4 steps here. I won't go into much detail of the physics behind it, but it's all in the DAVE Multibeam Sonar paper, which I linked before in the presentation. It basically has these 4 main steps. The first one is responsible for the point scattering model. The second one is the ray summation. The third one does windowing and correction. And the fourth part does the fast Fourier transform calculation. So we knew that there was room for improvement here because we saw that the main bottleneck of the code was actually in the CUDA wrapper. So it accounted for more than 50% of the total plugin time. By using NVIDIA Insight system, we discovered that that time was 434 milliseconds, also an average per sonar frame. And we also identified many problems by using these tools, which included many small memory transfers, some inefficient kernels, and repetitive allocation of memory, especially in the first 2 parts of the code, because they do the most part of the memory transfers. And they accounted for 86% of the CUDA execution time. Also, I wanted to highlight that all of these tests and demonstrations were done in a consumer laptop, which is my current laptop. It has these parameters here, so CPU Intel Core i7, 16 gigabytes of RAM, and also an NVIDIA GeForce MX 330 GPU. And these are also the parameters that we use for the standard testing for the sonar simulation. It's all here. So moving on, we knew that we had those problems and we wanted to know how can we further optimize it. So we knew that we had some memory problems and we searched a little bit on the internet and documentation to see how we can begin optimizing it. And we found these notes from University of California, which were very valuable in this process. And they listed some principles, which I will describe now. So the first one is to minimize data transfers. So we want to do as few as possible data transfers between the host and the device, even if it means doing stuff in the GPU that offer little or no speedup, if that means that we are avoiding transferring data back to the host. This is important because it can reduce overhead, latency, and synchronization problems too. So the second principle is using page-locked and pinned memory. So when using pinned memory, the GPU can access direct and do direct high bandwidth transfers, unlike when we use pageable memory. But we also have to be careful here because if we over allocate pinned memory, it can actually hurt performance. So this was all tested to not reach the point that it's hurting performance. The third principle is grouping many small transfers into a single larger transfer. This is because each transfer has a fixed cost. So if we do fewer transfers, that means that we can cut down on this overhead. So now I'll show the comparison between the old and the new code and the results we got from applying those principles and just doing a lot of tests in the CUDA sonar wrapper. So this graph on the right describes the top 5 CUDA API functions and their total time in the old and versus in the new code, but only for a single run, including initialization. So first we can see that the CUDA malloc and CUDA malloc calls remain almost the same, because at initialization we are not reducing the amount of buffers we are declaring or using less memory. But different from before, we are doing it only once at initialization and reusing those buffers in the following sonar frames. In the old code, we would allocate and free memory at every frame. But what I think is the most interesting part is that the CUDA memory copy time for a single frame was drastically reduced in about 94%, as you can see here. The old time was 122 milliseconds, and the new time for this function is 7.71 milliseconds. And that improvement in memory management is also described in this graph right here. So we can see that the host to device transfer total memory transferred per sonar frame decreased in about 80% from host to device, and in about 94% in device to host transfer. And also another good result that we obtained is that the average memory transfer per call increased notably, which was our primary goal. We wanted fewer transfers, but larger ones. And so here we can see that the average memory transfer per call increased from host to device and also from device to host. These are all the results we obtained, summarized between the four main parts of the code. So we achieved a 12.6% speed up in the code in the CUDA Sonar wrapper, which was before 434 milliseconds, and now is an average of 34.47 milliseconds per sonar frame on a consumer's GPU, which is the NVIDIA GeForce MX 330. And this graph right here shows the speed up. So this is the new total, is much lower than the old total here. This is also other results. So now considering the total sonar frame, which is the CPU plus the GPU part, we obtain an average of 2.51 Hz refresh rate on a consumer laptop and an overall speedup of approximately 1.91 times. And now I will move on to the progress updates and show some demo launch files, screenshots, and basically what you can do with the sonar. So here's a basic launch example we have in our repo. You can open it in RViz2 and look at the raw sonar data also in ROS2 topics. And it's also important to debug also and gather this data. So we have a write log flag that you can use to save CSVs of the data and further debug later. So this is another launch we have for the local search scenario. You can define the sonar location in the world you want to launch it in, and also its rotation. So here we are just moving it around to see how the resulting sonar image would look like. So as before, you can see the shadow of the object on the seabed. And also all the models here are available in Fuel, which is good because you don't have to download it locally. This is another launch example, but now using BlueOrl v2. So you can attach the plugin and the sonar model to the robots model SDF. But also don't forget to include the multibeam sonar system in the world so it works properly. There's all of this is listed in the documentation, so I can link it afterwards if anyone wants to try it out. So this is a summary of future works we think that are important. So first of all, we want to test it on other GPUs and other CPUs because for now we tested on my laptop and other consumer laptops. We also want to further investigate if we can improve the CPU part, which is now the bottleneck of the code, especially the parts constructing the sonar image, which take a long time. And we also want to compare it with other simulators and create more demo examples. Another idea is also to extend the multi-beam sonar plugin capabilities, for example, creating a 3D mechanical sonar. So this was the presentation of the project we developed this summer. I linked also our repository here with the ROS2 branch if anyone wants to try it out and create issues or PRs there. And here's also my email. I'd be happy to answer any questions about the project too. So that's it for my presentation today, and thank you for your attention.
Thanks a lot, Elena. Yeah, a round of applause for you and your mentors and everybody who, was part of the project. Yeah, it's very nice, to be honest. It's always very refreshing to see these projects that are a combination of like scientific challenges plus also implementation challenges. So very nice.
Mhm.
Questions for Elena? Oh, hi, Mabel. Please go ahead.
Hey, hi Helena, good to see you again. This is great work. I think the results look really thorough and the process seems rigorous. It's really cool to see. Since this talk is about performance, I was wondering, based on your observations on the consumer laptop, do you think it'll be a stretch to run multiple of these? Say, like, I want to simulate like 3 vehicles. Do you think it'll be a stretch to run on a laptop, maybe a higher end laptop? Or
Yeah, I think running on my laptop it would be very heavy. Like it can deal with one simulation, but I saw some delays when we tried, for example, using multiple plugins together and multiple physics plugins together. But I'm very curious to know how it would behave on high-end GPUs because also further accelerations because in my laptop, for example, it doesn't support half precision, and it was something that we considered doing, but we couldn't test it very well, and we could see further improvement in high-end GPUs. So yeah, I think for now I stretch in a consumer's laptop maybe, but in high-end GPUs, it would be very interesting to see how it would behave.
cool. I have a follow-up question. Do you think this will be upstreamed to the base Dave repo from Field Robotics Lab, whatever it's called?
Yeah, I think we do have a lot of, not a lot, but some work to do to wrap up the ROS2 Dave branch. Like its core functionalities are working, but I think Wansag and Rakesh want to do more demos. But the multi-beam part is pretty much done. But I think from more contributions and more people testing it, a lot of problems also arise. So I think it also depends on the issues that are being created and how we solve them. But I think it's pretty much okay from the testing that we've done.
Thank you, Mabel. Let me see who's first. Rakesh.
Yeah, great presentation, Helena. And just to follow up on the question that Mabel asked, I just wanted to answer that we are working towards the release and getting it upstream to the main Dave repository. We just have a bunch of benchmark cases that we want to wrap up so that people can have a full demo of spawning Blue ROE and moving it around using maybe teleop controls and also having to add multiple sensor plugins to it. So we're hoping to have it by the end of this year, like probably around Christmas.
but that's the plan.
Thank you. It'll be a good Christmas present for the community.
Hope so.
Thank you. More questions for Elena and their colleagues, mentors. I have two questions. So now, after your experience with CUDA and working also on sensors within Gazebo, do you feel we could use CUDA, or not necessarily the same exact approach, but just leverage CUDA to improve performance of other Gazebo sensors?
I think so, because before I didn't work with CUDA, but then I saw how much of it is not that hard to use. So even, for example, basic matrix multiplication, it can be much faster there, and also summation and reduction. So I think that a lot of sensors do a lot of parts that we implemented in CUDA. So I feel that yes, we could use CUDA in other sensors.
Okay. And also, out of curiosity, like when you were working in those optimizations for the sensor, do you have to consider the amount of bit RAM that your GPU had, or that's completely like independent? Like when you work with CUDA, you don't need to worry about that.
In my computer, I didn't have any problems, but it for sure was something that I had to analyze at the end, uh, especially when I tried working with more rays and more beams. So I think there's a saturation point where I would run out of memory for sure, especially in my laptop. But for the standard simulation we were doing, there weren't many rays. I think it was like 500 per 200 matrices that I was dealing with. So it wasn't that much memory. But it for sure was something that I wasn't used to looking at the memory transferring part, and the NVIDIA tools were very helpful to see like what was happening behind it.
Cool. Thank you. More questions for Elena? Jose.
Hello, Elena. Congrats. It's a really nice project, nice presentation. Question from my side that I'm totally ignorant in the DAVE community. I was searching for the repository, and there is one in the robotics. The main repository seems to be in somewhere called Robotics Lab. Something if you search in Google, but I saw that you were submitting your work to the Intelligent Ocean Engineering Laboratory. So the question is, which is the main DAVE repository that you in the community are using?
Yeah, so the ROS2 branch is in the IOES repository. The repository in the Open Robotics repo is the ROS1 Noetic and the Gazebo Classic one. So it's a working version, but not with the new ROS. And we are planning to upstream it to the Open Robotics repo. We just need to wrap up some demo and benchmarking cases.
Thank you. Yeah, I was searching Google, and I think that the main DAVE repository that you can find there is under Field Robotics Lab. So
Yeah.
that was probably the main repository that we host under the OSRF at some point, because there is no OSRF DAVE anymore, as far as I can say. So that repository, the Field Robotics Labs, is not been updated in 3 years. So I assume that the most active one is yours in the Intelligent Engineering Lab.
Yeah.
Okay. Yeah, let us know if we can help with figuring out which ones should be the active, and we can somehow mark or archive the ones that we are not using, so that people can find your work easily.
Mm-hmm.
Yep. Thanks so much. I have another question if no one has more. So it's like the sensor needs CUDA and a CUDA installation to work, isn't it? So it's not possible to run it without a CUDA installation, or it's able to work, or how difficult it will be to make it to work without a CUDA installation?
Yeah, for now it does not work without CUDA. So because the main part is done in a separate code, in a CUDA code, and I personally didn't try it out running it on the CPU, but I think it would be very slow. But we were planning to use not only CUDA, but also maybe Apple Silicon. We didn't investigate it further, but it would be interesting to work with other graphics card too.
Thanks.
We have time for any other questions if people have curiosity, now that we have Elena here. All right. Well, yeah, I'd like to thank you again, Elena, and yeah, congratulate for this awesome project. Yeah, hopefully this can land also and continue evolving because it looks pretty nice. So congratulations.
Thank you guys.
And we can wrap it up here. Thanks everybody for tuning in. Just a reminder that we will probably skip the end of December meeting because most of the people will be on holidays, but we'll resume our meetings in January. So thanks everybody and have a good holidays. Ciao.